Hello learners, welcome to section 6 of unit 1 in the course Introduction to Abstract Algebra. I am Unkaila Desrani and I am your course instructor for this course. In this section 6, we are looking at identity elements and inverses. Identity elements and inverses. You'll be learning more about identity elements and inverses of a function if it exists. By the end of this session, you should be able to explain an identity element. You should be able to explain an inverse, find an identity element if it exists for an operation. You should be able to also find the inverse of each element in the set on which a binary operation is defined. Definition 9. Definition identity elements. Let S be a set on which there is a binary operation star defined. An element Y of this set is called a left identity. If for all A in the S there is Y operation A equals to A, then we say that the operation is left identity. So the identity element Y here is on the left hand side. Similarly, an element Y is called a right identity if for all A in S there is A operation Y and the result is A. So the operation is also on the right hand side and that gives what we call right identity. So a binary operation defined on this set S may or may not have an identity element. So not always that it's having an identity element. An identity element has a neutral effect on every other element in X. So when the identity element is operated on any element on this as X, it's having no effect, that is neutral effect. If a binary operation has identity element, then each element in X has an inverse. So once there's an identity element, the inverse is also exists. Okay, let's look at these remarks. A binary operation may have a left identities which are not right identities and vice versa. So there's instances we can have left identities with no right identity. It's possible. Also, there might be many left or many right identity elements. So it can be more than one. It can be more than one. So there might also be no left or right identity elements at all. There might be an instances there will be no left identity, there will be no right identity elements at all. Great. Theorem 6. Suppose that S is a set with a binary operation star defined. Then that operation star has a left identity element E1 and also a right identity element E2. Then the left identity elements and right identity elements are equal, and then we say that E1 equals E2 and that becomes E. So when we have left identity elements in the operation or in the set and then the same function is having right identity element, then that operation is denoted by one identity element, that is E. So to prove this one, let's say E1 as usual, is left identity be a member of S, and then E2 right identity be a member of S. Then what can we say? E1 operation E2 equals to E2 in this instance. Okay, let me make it E1 so that I prove from that section equals E1 equals E1. Then here you can see that E2 is what we call right identity. Okay, so I'm using the right identity to prove. Also, if I have the same E1, let me call this equation 1. So if I have the same E1 operation, B2 equals to E2. What can we say about this? This time around, U1 operation U2 equals to U2. Then we can say that this is left identity. So U1 is actually left identity. Once U1 is left identity, and then we have U2 to be right identity. So by comparatively, or by comparing the two, equation 1 and equation 2, you can tell me that U1 is equal to U2. And the reason is that U1 operation U2 is equal to U1, U1 operation U2 equals to U2, and we can now denote that U1 and U2 by 1U, and that is proof for one operation is having both left and right identity elements, then we denote that one by G. Good. Definition 10. Suppose that a binary operation star is defined on a set S. An element Y, which is a member of X, which is both right and left identity, is called the identity element of S under star if it leaves every element unchanged. That is, if it's having a neutral effect. So if you use identity element of S under the star, for every A in S we have the left identity element equals the right identity element, and equals to A. So when the left identity element, let's say the left identity element and this right identity element, when both operates on the elements in S, then we get the same result. Whether both left or right operate on the element, the same result is obtained. Good. So let's look at example 27. Example 27. Identity element for the set of real numbers R under the addition and multiplication are respectively 0 and 1. Why do we say that? So here, if let's say let A be a member of this big R, the real number. So A is a member of this R of the real number. Now when I take 0 plus A, what do I get? I get A, and then A plus 0 equals to A. So left identity element operate on A, I get the same A. Right identity element operate on A, I get the same A. In this instance, we say that addition 0 is the addition, or 0 is the identity element for the set of real numbers. Similarly, for multiplication, if we have 1 times A, where A is a member of R, so here you can see that 0 is a member of the R. So 1 times A equals A, A times 1 equals A. For all 1 and A be a member of the real number of real. So you can say that left identity element operate on A, we get A, and the right identity element operate on A, we get A. So we can say that 1 is the identity element for the multiplication under the set of real numbers. Great. Let's look at example 28. Example 28. Binary operations is defined on the set Z of integers. That's set of integers by A star B equals A plus B minus 1. Find the identity element if it exists for this. So let's say that let E be the identity element. So let's say right identity element, the right identity element. So what can we say? You can say that A operation A, or no, A operation Y, that's right identity element, must be equal to A. But we know that A operation Y must equal to, let me call this equation 1, but we know that A operation Y equals to, put into the definition, is A plus Y minus 1. So let me call this equation 2. By comparing, A plus Y minus 1 must be equals A, comparing equation 1 to equation 2, so you get Y equals to 1. Okay, let's also think of y to be left identity element, then in that instance I can say that y operation A for left, so that is the right one we have done. For left one, y operation A must be equals A. So putting into that, it implies that when I put y operation A into the definition, I'll get y plus A minus 1, and the result is what? A. Result is A. So once the result is A, that is A. It means that when I solve this algebraic expression or linear equation, I'll get y equals to 1. So once the left identity equals 1 and then the right identity equals to 1, we therefore conclude that the identity element for this operation under the set of integers is 1. Okay, that is good. Let's look at the next. Exam 30 reads, a binary operation is defined by that's triangle down, is defined on the set of real numbers by A operation B is given here, where A, B, and R are all close, where A and B are members of R, and R is closed under the operation. To find the identity element here. So how do you find the identity element? The same thing, you use the same procedure. You find the left identity element, you also find the right identity element. So by calculation, your left identity element will be equals to 0 or divided by 1 minus 5a, and that'll be 0. And also you also find your other identity elements, so also get that one. Let's say u1 0 u2 equals to 0, so u1 equals to u2, and that equals to 0. To go through the hidden steps is just simple following the previous examples approach in order to shorten the video. Good. So the identity element here, since the left identity element is 0 and the right is 0, we conclude by saying that the identity element for this operation is 0. Inverse, definition of inverse. Inverses. Let's look at inverses. Suppose that a binary operation star defined on the set S has an identity element y. So if A, B, and S are all A and B are all members of S, such that A operation B equals to y, then B is called a right inverse of A. B is called a right inverse of A. When A operates on its inverse, you get the identity element. Likewise, if B operates on the A, we get the identity element. Then we call the B a left inverse of A. When the identity element, the inverse, operates on its objects, then the result is the identity element. Okay, so here an element can have no left or right inverses at all. Element may have no right. For instance, the number 2 has no left or right inverses with respect to multiplication on the set of integers. Can you explain this? Explain this. Great. Definition 12. Suppose that A has both left and right inverses, then A is said to have a two-sided inverse, or simply an inverse element. Like the identity element, when we're having both sided, both right and left, we represent it by 1. So when we have left inverse and you have right inverse, then we combine them by saying simply the function is having an inverse. So learn how to do this proof. Example 31. Consider the operation star on the set of integers defined by the operation star here. A operation B equals A plus B. Show that each integer has an inverse under this operation. So how do you show that this integer has an inverse? So first, before you can find the inverse, remember when an object operates on its inverse, the result is identity element. So first you find identity element, so you let E1 be the left identity element, E2 be the left right identity element. So by calculation, you get E1 equals to E2, and the result here, when you solve it, you get 0. So find it. I know you can find this one. The identity element is 0. Once the identity element is 0, then we are free. We can now find the inverse. You can find the inverse. So let's y be an y which is a member of a real number. Yes, let's y, because the question is consideration on so integer. So let's y be a member of z, and also x also is a member of z. Here y is the inverse of x, so let y be the inverse. So this y is the inverse. Let y be the inverse of x. Then what can we say? If y is the inverse of x, then you can say that x operation y equals, based on the definition, you get x plus y, and this is the same as the identity element. And what the identity element is 0. Is 0. Similarly, we can also find y operation x, and the same thing, you get the same result. So here we are finding the inverse. We are saying let y be the inverse. So I can make y the subject here, and y be equals to negative x. Therefore, the inverse here showed that each integer has an inverse under this operation. So the inverse is negative x, negative x. So any value you put, you negate it, that becomes your inverse. You get the object, you negate it, you get your inverse. So that is the inverse for example 31. Example 32. A binary operation is defined by this definition here, and we have been asked to find the identity elements and then find the inverse. So by calculation, the identity element is so simple. You get E equals to 0. U1 equals to U2 equals to 0. You know this one already. Now we have to find the inverse. So let's, as usual, y, which is a member of the real numbers, be the inverse. So be inverse. Then what can we say? Then you can say that x operation y, so y the inverse of x. So x operation y will be equals to x plus y minus xy, and this will be equal to identity element, and the identity element is what? Is 0. So once this is equal to 0, we can equally solve for y. So by solving for y, you get y equals to minus x, or divided by 1 minus x. You factor, you group like terms, and then you factor, or can factor y out here, then you divide through by the coefficient of y. So here you have to define by telling us that x is not equal to 1. So once x is 1, the function is undefined. X is not equal to 1. So this is the inverse for this question. So in this session, if you look at identity element and also inverses, and we say that if you have left and right identity elements, then represented by E, and then once the function is serving identity element, then there's an issue of inverses there. That function is having an inverse.